What is CURE? So CURE is a project that requires undergrads to conduct scientific and mathematical research. This project also helps to develop communication skills as well as collaboration skills with other peers and figuring out how to work together while pursuing a career in STEM. The CURE project helps students to better understand what it means to conduct scientific research and do it on their own. And this will help give them better research skills for the future and make them more confident. To start, I will be talking about a Young diagram. It's also known as a Ferris diagram, and it's basically a chart almost with left justified cells. This actually created a problem for us because we wanted to count them by hand, and it was really tedious in the long run. A standard tableau has integers that increase in each of the rows as well as the columns. In a semi-standard tableau, this allows for repetitions of integers, and the rows can only be non-decreasing. A skew tableau is the result of moving a piece of a Young tableau, which itself follows all of the constraints of a Young tableau. In a skew semi-standard Young tableau, it is in a skew shape or subpartition, where the cells are filled with integers in a manner that satisfies the constraints of a semi-standard definition.
Hello, so I'm going to show you our method of counting semi-standard skew shapes and n-by-n matrices. For example, right here, we have a matrix that satisfies the semi-standard definition of weakly increasing rows and strongly increasing columns. So when we make our cuts in this matrix, every cut we make will be a semi-standard skew shape. Weakly increasing rows, strongly increasing columns. This could be a skew shape right here. This could be a skew shape. But then also we have to note that here are two 4x4 matrices. We want to count matrices even if they are adjacent, or even if, for example, this, we want to count this shape, right? The confluence between those two shapes, so that we get all the 4x4 shapes within this n-by-n matrix. This shape right here is an example of why we chose to represent semi-standard in the fashion we did over here on the left, is because this is a semi-standard. As you can see, we have weakly increasing rows and strongly increasing columns, but this is not as elegant a representation of semi-standard as we have on the left. This matrix does help demonstrate that two adjacent matrices are distinct. So this 2x2 matrix and this 2x2 matrix are both distinct shapes, and we want to make sure to count all of those. To show some more examples, further edification, each skew shape we take needs to fulfill the semi-standard definition of left justified. This right here, we have a pink skew shape. This is left justified. For left justified, everything needs to align well on its left side, where here, in this gray staircase example, this is not just left justified. Everything would have to be aligned on the left. So this is an example of left justified, and this is an example of a non-left justified skew shape. We're not going to count this. Here are some more examples, shapes that we will be counting that follow our the definition or the precepts set by the semi-standard definition. Now I'll show you how we go the actual process of counting our skew shapes. Here is our most basic shape, a 2x2 matrix, and I will now show you how to count that. It's important to note that we will not count, for example, n by n by n. We will not count the entirety of the shape as a skew shape. For example, we can have an n by n minus 1 shape. If we take this shape right here would be an example. And here you can see all the shapes that we took out, and I tried to color code it to demonstrate exactly how I'm cutting up this 2x2 matrix. And you can see some patterns. You can see that we have 5 shapes that we can take out of a 2x2, and that we have 2 vertical 2x1s here and 2 horizontal shapes here. We're going to note that pattern. So now we're going to move on to a 3x3 matrix that we have here. One thing that we can do, this is as you can see, this will become a laborious process as we increase the matrix size. So what we can do is we can use the previous matrix in order to count in the recursive-like fashion. So let's count how many 2x2 shapes exist in this 3x3 matrix. Well, there's a 2x2. Here's a 2x2. Here's a 2x2. Here's another 2x2. So we have 4 2x2s and this 3x3. So now that we know that we have 4 2x2 shapes within this 3x3, we can calculate how many shapes that is by taking the 4 2x2 matrices that are contained within this matrix and multiply it by the amount of shapes that we can count from a 2x2 matrix. That number is 5. So already we have 20 shapes. Now I'm going to show you, to drive this all home, how we go about counting a 4x4 matrix, the skew shapes. Now, as last time, we're going to want to count how many 3x3 matrices is contained within this shape. Well, we see a 3x3 here. I see another one here. I see another one here. And I see another one here. So note, we have 4 3x3, 4 3x3 shapes that are contained within this 4x4 matrix. That follows our pattern of 4 2x2 and a 3x3 and a 3x3. So now we go about counting the shapes that are unique to our uh, our new matrix, our 4 by 4 matrix. So, for example, we're not going to want to count this shape right here because we've already calculated it down here recursively because that shape uh, has come from a 3 by 3 matrix. Um, and just like this shape is also calculated, we saw that in our 2 by 2 matrix, so there's no need to count those kind of shapes. The shapes we're looking for is a shape like this. We have not seen this shape before. So here we note that we have 15 shapes within a 3 by 3 matrix. We have counted that we have 4 3 by 3 matrices in this 4 by 4 matrix. And so we can down here we can multiply and we get 60. Well, now we need to start counting how many shapes uh, are we looking at here that we haven't already counted. For example, we've counted this shape already because that shape showed up in our 3 by 3. We counted that. We also counted a shape like this because that we saw that back in our 2 by 2. So the types of shapes we're going to be looking for in this is something that we haven't seen before. We haven't seen this shape. So yeah, because this shape has not is impossible in a 3 by 3 matrix, but now we see it we will see it in our 4 by 4 matrix, and we'll also see it moving forward in our 5 by 5. We can look at this shape that I'm highlighting here. That's new. We haven't seen that before. So we're going to get, looks like 3 vertical columns. That I'm going to shade in right here. And so we can count these. It might be difficult to see, but we got 3 vertical shapes that we haven't seen before because these are 2 by 4s. Those are, and we couldn't get those from counting 3 by 3s or 2 by 2s. So we're going to look for more shapes that are in this fashion. And I believe my group counted 7 shapes that we didn't see in our past counts that would satisfy our definition. So that means we have about 67 shapes that satisfy our definition of semi-standard, skew, shapes, and these shapes are not K by K. They are not, we will not count this entire 4x4 matrix. In our counts, you can see here that there are no k by k shapes counted. And as you can, and down here, and you can see if you look up here at our 2x2 counts, there are no k by k shapes. So the shapes we are counting follow this definition of semi-standard, weakly increasing rows, strongly increasing columns, and there are no k by k shapes. In here, our 3x3, we have not counted any 2x2 shapes. And in here, we have not counted any 2x2 shapes, any 3x3 shapes. And we do not, and moving forward, we will not count any 4x4 shapes. So now you should have the understanding of how to count, and I hope you can try your luck on a 5x5 matrix. And check our counts. Thank you for enjoying our lecture on calculating semi-standard skew shapes. Just to reiterate, we can count skew shapes in a recursive-like fashion if we know the amount of shapes, skew shapes we can pull from a lower n by n matrix, and then we count the shapes that are unique to the n by n matrix that we are currently calculating. Some few facts are sometimes dots are used instead of cells in Young diagrams. And for semi-standard Young tableau, the Schur polynomial can be expressed as a sum over the semi-standard Young tableau. Some difficulties we had were calculating counting the skew shapes by hand, and also understanding which direction to take the project. These were both remedied by consulting with Professor Doss. Ultimately, this was a fun experience that pushed us all to think more critically about higher level math. Thank you.